bottom part, and make it so it resembles a single term square, and then kind of split up the top part so it looks like
I think. Wait.
I don't know if that ever works.
Actually.
That's what makes
Right.
all of this hard. The things we know from before and the way we break down the problems before doesn't always go anywhere. But then, like, I could add an X to the top, and what you said might work. So, like, what works and what doesn't work is subtle. Yes?
I could be wrong, but that looks a bit like inverse tangent.
Yes. Where it's always repeating on words. The derivative of inverse tangent.
Yeah, sorry.
Why is that? What is the derivative of inverse tangent? I didn't like memorize this chart last night. You'll need it some for 4-4, and you'll definitely need it for the final.
I'm guessing it's 1 over 1 plus x squared.
Yep. So the hard ones that show up in this section, I shouldn't say hard ones, but the ones that, like, you're tempted to break it apart and try other things, but they don't really split nicely. Because, like you mentioned, try to make it a perfect square, but I would need a plus 2x in here. And I can't do like plus 2x minus 2x. So the ones where you're almost tempted to break algebra or try to break it apart in some strange way, typically it's an antiderivative, or typically it's the derivative of some inverse trig function. Because what do inverse trig functions do? They gave you things like this, or 1 over the square root of 1 minus x squared. Like some of these fractions that don't look quite nice, but aren't too bad, it's because they're coming from an inverse trig function. So if I know this, how do I use this over here? Because this is a constant, you can move it outside. So I can never move an x from inside my integral sign to outside my integral sign, but I could move the constant 4. So now what? Do we know the antiderivative of 1 over 1 plus x squared?
What's inverse?
So if the derivative of this, of inverse tangent, is this function, that means inverse tangent must be the antiderivative of this function. So we know this is going to be what? 4 times, this would give me inverse tangent of x plus c. Why did I write the plus c this way? So this is the one that's kind of subtle. The integral sign is what gives you the plus c. So if I had to find all possible antiderivatives of this, it would be this, right? And then, what do I get here? This plus 4c. And when you go to check in the back of the book, it'll just say this, which is a little bit fishy, isn't it? If you want to make it an equal sign, I would say call it C tilde or something. But then why would the other answers work?
C is any constant?
C is absolutely any number, right? It's a constant. If C is arbitrary, 4 times C is still an arbitrary number, right? Which means I don't really need to account for the 4, I can just put any generic constant there. If C is arbitrary, 4 times C is arbitrary. There are courses where this comes up, you have to be a little careful. It's like if C is arbitrary, C squared would be an arbitrary non-negative number, because it can never be negative if it's squared. So sometimes when you manipulate the constant, you have to be a little careful. It goes from like any positive or negative number to any positive number, depending on what you do. But for one like this, if this is arbitrary, this is arbitrary. How can you check this? If I were to take the derivative of inverse tangent of x plus c, or the derivative of 4 times inverse tangent of x plus 4c, both of these would be the same thing, 4 over 1 plus 4. Because the derivative of c or 4c both would give me 0. So, for the first time in your life, you're allowed to not really distribute. Or it looks like if I could have dropped these parentheses and I'd gotten the right answer right. I could have gone from here straight to here. And if I did that, I likely wouldn't put the tilde on it, because why would you put tilde? You just put plus c. But it's because they're equivalent to each other. The notation says find all possible antiderivatives. All possible antiderivatives would have this form. Any questions there? It's a little bit. It's both subtle and not. You can't just basically write all your answers and write plus c, which is almost true. It's when you get rid of the integral sign that you add plus c. Kind of like when you stop writing limit, when you plug in the x value. You stop writing integral sign, you write plus c, because this plus c is built into this notation. Any other questions on that one? Any comments? All right. Now one that's both related and significantly harder. Everybody likes taking antiderivatives. This looks almost the same, doesn't it? Yes.
Could the bottom potentially be separated as... No, wait, I was gonna say difference of squares and then...
add two things, yeah, it's not difference of squares because you're adding them, messes up. I need a cross term if I want to do anything. There is no cross term. Like I would need a plus 2x somewhere in there. Do what you want. Or 4x. 4 out. Whatever. Because I'm adding, I can't just move the 4. Can't cancel the 4 from the top. Like I'm really stuck in order. Adding in the base always makes things harder. If you add the numerator, you can split it up, right? And it's 2 different fractions. But it doesn't work with the base. Yes, that is what I'm going to do. But I have to be careful how I do it. So, what does it look like we should be able to use? Plus, why did I just now write this example? It does somewhat look like this, doesn't it? But I put the 4 in the wrong place, so I can't easily do it, but it looks similar to this idea. So now the goal is to make this one work. So, which is why I'm doing this in class. I don't remember if this comes up exactly in the homework. I know that problem's in the book. I don't remember if it's one we assigned. But it's always worth talking about. If I move the 4 out, I get a 1 here. I also have to take the 4 out of the x squared, right? So what happens here? I have to write x squared over 4. Is that the same thing? So like I can factor a 4 out, but then I need this to still get here, so you have to divide by 4. Yeah, anytime you write something, go ahead and multiply it out and make sure it checks. It's real quick to check something on that step to do it. Usually the other direction is easier to verify. This is In some ways, this looks a little bit nicer. Because I can also just make this what, x over 2 squared? So now I have that 1/4 factored out of everything, or 4 factored out of everything, I can move the 1/4 outside. It's looking a little bit better. Except I don't quite have x squared, I have x divided by 2 squared. So like I got the 1 over and a 1 here. And I am adding something squared, but it's not quite the right thing. Yes.
Maybe we could turn x over 2 into u?
Yep. If we do use substitution, I'm not quite teaching it that way, but that's essentially what I'm doing. Alright, so we're going for this. But I have that 4 mixed in, but it's inside the part that's squared. So like that divided by 2 is very much attached to x. So it's like I'm inserting a function into what I really wanted, right? It almost looks like a chain rule. Or like if I were to do something, I would probably need a chain rule because I have x divided by 2 and not just x. So what's the derivative of inverse tangent of u? It'd be something like this. What am I letting u be here? If I wanted to try to use this out here. So you said let u equal x over 2. So then u prime of x is what? 1/2? So if I look over there, what am I missing? I'm missing this factor of 1/2. So what do I really want? So I have my 1/4 sitting here. I have this integral. I really want there to be a 1/2 right here. Yeah, right. I really want that right there, right? Why would I want that right there? I can put that right there. This looks like 1 plus 1 over x over 2 squared times d dx of x over 2. Why am I shooting for that? Do I know the antiderivative of this? That would be the inverse tangent where I just have to use a chain rule to get the derivative on the outside, or the extra little derivative piece that's multiplied. But to do that, so I need a 1/2 here to go with this part to correct down here. And I just multiply by 1/2. Like, what's the difference
Wait.
between this line and this line? All I did was multiply by 1/2.
Wait,
Yes.
maybe because when you took, when you undid it, 'cause when you originally did the chain rule, maybe there was a 2 coefficient, and then you multiply by half, and then that canceled out.
Gotta do this.
Huh.
So like I need a 1/2 right here. I can put a 1/2 there as long as I also multiply by 2, right? 2 times a half is equal to 1. Didn't change anything. And then what can I do with the 2? Do I need the 2 inside the integral sign?
You can move it out.
Because it's a constant, I can actually put the 2 right here. So I'm allowed to add a factor of 1/2 if I'll also multiply by 2, right? So when I do that, that 2/4 becomes a 1/2. So now I have this formula. So I had a 4 sitting here that I couldn't do anything with. If I'm going to undo anything, I needed to attach the x, because then I can make it a chain rule problem. So I factored out the 4, which got me this x over 2 sitting here. So it's like my inside function was x over 2. If I had an inside function, I also need to multiply by its derivative if I'm going to then work backwards. So I want to look at this as a chain rule. Or I want to look at it as, I use this formula, but with a chain rule attached to it. Which means I need u prime of x sitting there, I need a 1/2 sitting here, so I can write it this way. Because then, what's happening there is this times its derivative. So now it looks like the chain rule. But then in doing all that, I can't just put a 1/2 here, I need to balance it out with a 2. So in all this, this is the exact, or this part is exactly equal to where it started. Why do I care? What is my antiderivative now?
Inverse tangent of x over 2 plus c.
Yeah. And then what do we always do at the end?
Plus c.
Yeah, what do we do right before we panic and turn in the test or quiz? Look at everything and write plus c's all over the place. Hopefully it's the right places. It's always fun on the final where somebody will remember at the last second, oh, I forgot about plus c, and then they write it on like every page. And before wasn't every page of the Yes?
If we did use substitution on the quiz or the test, would we still get points on it for it?
That's fine.
Okay.
I'm not sure some of the Khan Academy videos don't include it. Yeah, substitution is the guaranteed way to do this. So I'm doing it by recognizing it as a chain rule. Like if you're undoing the chain rule, there's another technique to do it. I'll write on the board real quick. All right. Last thing we do is always check. What's the derivative of 1/2 inverse tangent of x over 2? I don't need to work out the plus c, right? I know that's 0. So that's going to be 1/2 times 1 over 1 plus x over 2 squared times the derivative of x over 2. So 1/2 times this times 1/2. So I get the 1/4. This sitting there. Get our answer check. It actually checked this line, didn't it? That's another fun thing. When you go to check, it's usually going to check one of your in-between lines. It won't always be the top one. If I wanted to make it look like the top one, what would I do? I'd have to distribute the 4 back. Then it checks. That's just redoing what I'd already done. A lot of times when you go to check, you get the form before you really start taking the antiderivative. big check. And this is, in my mind, this is as hard as this ever gets. Like, this is basically the worst it can ever be. It's because it's hard to see the chain roll apart. And like inverse tangent's not the one we usually think to go to. Any questions on that one? Other than the one I haven't answered yet. You'd ask, did I do substitution? So, there's a section in chapter 5 that tells you how to do substitution formally. It's the exact same thing we're already doing. So how would I do this one? So, sadly, unless I do something else, I'd have to recognize, I'd still have to get to this step. Like, I still have to get there. You try substitution any other way, it's not gonna work for this problem. So the problem with substitution, you get multiple choices to do, and most of them, this one you could easily go down dead end. I can't even show you that, I guess. But now we would say this will look similar. Let u equal x over 2. So then what is the derivative of u? 1/2. So what that says is, now we kind of cheat a little bit. And we say du is equal to 1/2 of x. So we actually break apart our differential. And then the last thing you can do is say that means 2 times du is dx. So I know what u is, and I know what dx is. Why would that matter? If I go over here, instead of writing x over 2, I write the letter u. And now instead of writing dx, I write 2 times du. Alright. So then what is the antiderivative here?
Inverse tangent of u.
Inverse tangent of u. So this says the variable I care about is u. So if I were going to undo this, the antiderivative is the inverse tangent, but I'm using the variable u now. So then what's the last step?
Substitute
Go back to x. So what is the whole idea of substitution? Says this problem is hard with x. Use some letter u instead, rewrite the problem, solve the easier one, and then go back again. So it's a transformation of the problem to make it easier. Alright, we got the same answer. And really, it almost looked the exact same. What would have happened, since I'm saying you're allowed to do this if you want, what would happen if I did something like this? Because the whole idea of substitution is pick something to make the problem easier. Man, I got rid of the 4 and all that like this, call that whole thing u, that would be easier, right? So then you get du dx is 2x. So du is 2x dx. So I can solve for dx. Now when I go to plug this in, what do I get? We say call all of this u. And then replace dx. And now what's the difference between what happened here and what happened here? why did we say we knew this antiderivative? Because everything depended only on u, and I could just write down the formula, essentially. Like I could have taken this formula and everywhere written just u. So I knew that antiderivative. What about here? What's going wrong? This says my variable needs to be u. And I have an x sitting here. I can't have both u's and x's in the same problem. Here I started with all x's, did the substitution, had only u's. So everything worked, and then I could solve this problem. Here when I tried to get rid of the x's, it kept them. So because there's still an x here, and that basically means u equal 4 plus x squared doesn't work. The whole technique, or the technique failed. I can't use that choice. That doesn't mean there isn't a choice that works better, it just means the choice I made at the beginning was wrong. I tried to make the problem too easy. And when I did that, I broke the problem. Why would that have been easy? What's the integral of 1 over u du? Yep. Natural log of the absolute value. So how did it work? My answer would have had a natural log in it, which is very much wrong since my answer should have been inverse tangent. So you are allowed to use this technique. I will count off if you show all the steps, but you also need to convince me it's working. And if it's not one you know well, it's easy to make a wrong choice and not be consistent somewhere and mess up. So really the idea is always be consistent. I can either use x's or I can use u's, but they can't both be in the same problem at the same time. All right. So that's another way of really doing the same work, right? If you look at this solution and this one where it works, it's the same, they're working for the same reasons. And really when I motivated it, I was almost thinking substitution. And then we forget, all substitution means is we did a chain rule. Right? So really I'm just making it look like, the way I'm explaining it is make it look like a derivative we know, where you multiply by the derivative of the inside part. Now I can see this was just a chain rule. So when I undo it, I'm just plugging something in here for an inside function. Right? That's the one I'll consistently use. But I know some of the external videos definitely go through substitution. And they are considered the same topic in a lot of ways. Right. Any other questions on that? Oh, no, I can spend that long on one example. It didn't look too bad. Other than that, man, you move the 4 from one place to the other and this becomes way harder. That's not like derivatives. In derivatives, if you move the 4, would you care at all? It would have been, what? Same rule either way. Derivatives are always, in some sense, straightforward in that there is a next step you can take. Going backwards, it's not always clear because that next step you took really changes what the output looks like. So here we're given the output, we don't know how we got there. We don't know what steps were taken along the way. So we're trying to figure out what steps were there. And typically the worst ones mean there was a chain rule involved. Or the one we had at the end of class yesterday, it looked like a quotient rule was in there, so try a quotient rule. For the most part, it's always a chain rule. The ones that are like a clear quotient rule, in some sense, when it looks that awful, that's your red flag to get a quotient rule. These are the most subtle, where it looks harmless, but can really include a lot more work. Alright, one that's a little more straightforward. What can one find the indefinite integral of x squared times x cubed plus 4 squared? You had to take derivatives, or, yeah, if you had to take derivatives, what would you do? Okay, so let's see if I get the other guy. So pretend this was take the derivative, not the inverse. What would you do?
Product rule?
Hmm?
Product rule?
Product rule, because I have this times this. Do we have a way to undo the product rule?
But that's not a product of the product rule.
You have to do the product rule. My first thought was I don't really want to do the product rule. Is there a way to avoid the product rule? Expand everything? Why would that be nice? Then all I need is a power rule. So it's kind of the same idea. Some of these simplify first. It's a little bit nicer here in that you don't even have options. We don't really know how to undo the product rule, so I should probably expand first. All right. So if I expand, this is what, x to the 6 plus 8x cubed plus 16. So when I multiply by x squared, I get x to the 8 plus 8x to the 5th plus 16x squared. So I want to take the integral of x to the 8 plus 8 times the integral of x to the 5th plus 16 times the integral of x squared. So now what? You say I just do the power rule, right? How does the power rule work for integration? Add first, then divide. So add 1 to the power, I get x to the 9th, and then divide by it. So this is going to be 1 over 6 times x to the 6. And then this one is 1 over 3 times x cubed. And then once I get rid of the last integral sign, I need a plus c. So I'm going to write this in the dumb way for now. Do I need a plus c?
No. You have, yeah, you still have
Okay, it's built
integral.
into that last integral sign. So when do you write plus c? It's when you get rid of your last integral sign. Before that, it's built into your integration symbol. All right. I haven't finished the problem yet. This still represents the entire family. The plus c is buried in here. Okay. So really, I wouldn't show that step. I would have done this already. But once I do that, I need plus c. And then once, I guess you could simplify this a little bit. 8 over 6 is 4/3. Is anything else simplified? 16/3, some kind of stuff. So that's my answer. What should I do now? Always check just in case. So that was what? 1/9 x to the 9 plus 4/3 x to the 6 plus 16/3 x cubed. So I take the derivative. I get this. So x to the 8 plus 12x to the 5th plus 16x squared. And I can't add that times 1. That's 8. We make all the calculus look bad and then mess up the derivative. Especially with definite intervals. Did it check? What line did it check? It's actually the one in the middle. As long as it checks one of the lines, you're good, right? Any question on that one? That's like what we look for. It's only the power rule. But it's easy to mess up the power rule, especially when you do it in reverse order. That's why I say always take the derivative. This is the part we kind of go on routine for. Right? This is what we know how to do. This is what we practice. If you do this every time, you'll catch any mistake you made here going backwards when you undo it. Right? Like do the one we're most comfortable with every time to make sure you don't make a mistake when you're coming up with the answer. All right, one more. So I want to find the antiderivative of 6x squared times sine of x cubed plus 1. Yes.
Wouldn't that just be the chain rule?
Do what?
Wouldn't that
Chain rule?
just, yeah. Because the derivative of x to the third is 2x squared. So then you just,
This part's annoying looking, right? Can I do anything to simplify sine of x cubed plus 1?
and then you also have an x.
Like, I can't break that apart in any way, right? No
Hmm?
matter what, there's an x cubed plus 1 inside that sine function. I can't distribute it, can't do anything strange there. So when you see something like that, what should that tell you? Treat it like an inside function. So if I, basically this one, here it was subtle, where I had an inside function, which is why I wanted to spend a lot of time on that example. Here, when you look at this, when you see this part, you think that has to be an inside function. So then what is the derivative of x cubed plus 1?
3x squared.
3x squared? Does that look anything else like what's sitting there?
I mean, if you divide the 6x squared by 2, but then take the 2 out, like,
I could write it like this. So now it looks more like a chain rule. If I want to make it look exactly like the chain rule, move the 2 outside. And then instead of writing 3x squared, say that was the derivative of x cubed plus 1. So now it looks like the result of finding the derivative of a trig function, then times the chain rule because I had x cubed plus 1 inside. Okay, so now this looks like, I don't know exactly, or I kind of know how we got there. I got there from using a chain. So what is my outside point? My outside thing is the sine function. What is the integral of the sine function? Negative cosine of x. Which is annoying. It's opposite of what we always think, right? It's easy to say cosine. Why is it negative?
well, because the derivative of cosine is negative sine.
Yep. So, and then if you miss this, when you go to check, you'll be off that negative sign and you'll know, hey, I should check this. Or relook at this. So what do I get? -2 cosine. Now instead of writing x, I write my inside function. So if I want to check, find the derivative of -2 cosine of x cubed plus 1. So I get -2 times the derivative of cosine of x cubed plus 1. Derivative of cosine is negative sine. Then because the chain rule, I have to multiply by this derivative. So what happens? -2 times -1, I get a +2 times sine of x cubed plus 1 times 3x squared. And that checks, right? And I can multiply that out, get the, and move stuff around, get 6x squared in front. But at this point it checks, right? That last line you go on autopilot, that was much easier than how we came up with our answer. So I made a mistake here and written plus instead of minus. I'd get a -2 here, and that would remind me, hey, I probably missed a positive or negative sign. Right, that's how you. We can always go through and explain why, but then usually it's the same, similar things over and over. If you miss a negative sign, you catch it when you check, and then you know to go back and fix. Any questions on that one? Thankfully, I don't know, in this section, there's a lot of examples. It's like that when we told you, hey, go take derivatives all week. And I wish you'd taken derivatives for 2 weeks so that this would be infinitely easier. But thankfully, there's no other content in this section. Except, I guess we always give you a word problem at the end, so I was going to do a word problem. There's one set of examples we always kind of relate back to, and it has to do with physics. So I can throw a ball, find out when it lands, or something like that. So I had one of those I wanted to look at real quick. Alright, so the last example. A ball is thrown in the air. Off the building at 8 feet per second. And the building is 64 feet tall. When does the ball hit the ground? Anytime you think, what we're going to do next, go ahead and pick something random. We don't want you to feel too comfortable. How is any of this related? So there's one thing I'm given. Well, besides the story. My acceleration is -32 feet per second squared. Right. Anybody know where that's coming from? Thanks, given. That's the acceleration due to gravity. Gravity has a force where, or the force of gravity basically says you're going to accelerate at -32 feet per second squared. So what happens to the ball? When you let it go, ignore air resistance, what's the only force acting on it? Gravity is pulling it down. So because of gravity, I have a constant acceleration of negative 32.
So this is not something that was given to us, this is just like a Earth gravity thing?
Yes. Yeah, supposedly this is known. I think they usually give it to you as a hint. So why does acceleration matter? This is going back, we've done this before. It's been a long time. I really want to know what is my height, right? Slash position off the ground. So then what is my velocity? This is the derivative of the height. And then what's acceleration? The derivative of the velocity. Alright. So this is our background. I'm given my acceleration is negative 32. So then what's my velocity? It would be based on the antiderivative of acceleration. I know acceleration, I want to find height, right? Except there's a velocity in between. If I know acceleration, the antiderivative of acceleration would be velocity. So I need to know what is the integral of negative 32. What is that? What function has slope at negative 32?
Negative 32t plus c plus c.
Plus the constant. Alright. I actually know my constant. What is my velocity at time 0? It's thrown upwards at 8 feet per second. That means my velocity is initially 8. So what does that tell me? If I compare these two, 8 is equal to negative 32 times 0 plus c. C must be 8. So my actual velocity is negative 32t plus 8. In general, there's this arbitrary constant, right? But it's not arbitrary here because I know my initial velocity. I know something about it. Whenever you're given numbers like this, it actually tells you a little bit more about it. So then, basically out of time, what's my height? I'd have to take the integral of the velocity. The integral of this would be negative 16t squared 8 times t plus another constant. What would that constant be? It says I start at 64 feet high. If I plug in 0 for my height, I would just get constant. So c must be 64. So my actual one is negative 16t squared plus 8t plus 64. And then what did it say? I want to know when the ball hits the ground, right? How do I solve that? This is my height for all time starting at time 0 until I hit the ground. I want to solve h of t equal to 0 for t. If I always know the height, if I set that equal to 0, it tells me when I hit the ground, right? And when I do that, this is quadratic, so there's two solutions. One is positive, one is negative. Which one do I pick? That's the positive one. So if I were to graph h of t, it looks like this. So I want to find that value over there to the right. Right, negative 16t squared. That was a parabol opening downwards. And really what this says is my slope is positive 8 at the initial time, so first the ball goes up, then it goes down. I'm finding that x-intercept. Right. I have the full solution to this posted online, or at least I will 2 minutes from now. Alright, so remember this homework is due tomorrow and then we'll start more time.